All right, so here we want to look at how we can use our knowledge of vectors to describe a line in two-dimensional or quite often three-dimensional space and different forms of an equation. And so I want to mostly deal in three-dimensional space here just because we've done lots of lines in two-dimensional space. And so this equation here describes a line. And this is a vector equation of the line. And so what does this mean? Well, any line in three-dimensional space can be described by a point. So this represents a point. Or a position vector, plus some constant times a direction vector. It's kind of like the idea of going way back with lines in which you can describe, as long as you know a point and the slope or the gradient, you can visualize a line. It's related to that idea. And so let's take this equation though. Instead of writing it in these with I, j, and k, let's write it with some vectors, and so, or with column vectors. And so I'll say R is the same as -1, and I'm just looking at this part right here. So I is -1. There is no j there, so that means that's a 0, and the k is 3. So this represents a position vector, or you can imagine a point on some line in three-dimensional space. Plus, let's try that again, plus lambda, some constant, times the direction vector. And this right here is the direction vector. It's describing the direction of the line in three-dimensional space. And I'll write it as a column matrix, a column vector in a matrix here. So 2, -1, -3. All right, so again, this is what we call the position vector. This is the direction vector. That said, if this vector R is the line, if we think of that as being coordinates x, y, and z, then we can say that x equals -1 plus lambda times 2. So to clean that up a little bit. Oh, it's not actually letting me go back. Why? Well, that's not very nice of you, OneNote. It's not letting me clean this up. All right, there we go. That's it. I can say that x equals -1 plus lambda times 2, or 2 lambda. I can do the same thing for all three dimensions. I can say y equals 0, so I can skip that, plus lambda times -1, or just y equals -lambda. And then z equals 3 plus lambda times -3, or z equals 3 minus 3 lambda. Keep in mind this lambda here is just some constant. And so what I have here, these three equations, we call the parametric form of a line, in this case in 3 dimensions. Well, each of these equations has the same value of lambda, and it's some constant, but it's the same constant, which means I can isolate lambda in each one of these quite quickly. So this equation here, if I isolate lambda, I get x plus 1 over 2. This equation here, if I isolate lambda, I get just, should I say this equals lambda? Over here, I get just -y equals lambda. And likewise over here, if I isolate lambda, I can get -z plus 3, or 3 minus z over 3, or some form like that, isolating lambda. And since these all equal the same thing, that means these three different forms all equal each other. So I can write this as a single equation, where I can say x plus 1 over 2 is equal to -y, which is also equal to 3 minus z over 3. And this one equation with 3 parts to it, we call this is in Cartesian form. So this is the Cartesian form of a three-dimensional line. This here is the parametric form of a three-dimensional line. And this here is just the vector form of a three-dimensional line. They're all equivalent. All right, so that's done. Here I have a line represented in vector form. And again, this is the position vector. This is the direction vector. All right, I want to show that this point here is not on the line and this is. So how can we do that? Well, one way is let me write this equation in Cartesian form, which is a nice way for substituting x, y, and r, because again, each of these are x, these are y's, these are z's, I should say, not x, y, and r. And so if I write this in Cartesian form, well, first let's write it in parametric form. And again, imagine all of this to equal some x, some y, some z, and so x is the same as 1 plus lambda times -2, or I can say x equals 1 minus 2 lambda, just like we did before. Likewise, I can say y equals just lambda, and I can say z equals -3 plus 4 lambda. All right, and again, since all these lambdas are equivalent to one another, if I solve for lambda, I can put this into Cartesian form quite nicely. And so solving for lambda, the first one I get lambda equals 1 minus x over 2. The second one I get just y equals lambda, or lambda equals y. And the last one, I get z plus 3 over 4. And since these all equal the same constant, these equations all equal each other. And now that's written in a moment in Cartesian form, so 1 minus x over 2 is equal to y, which is also equal to z plus 3 over 4. And now I can quite quickly check these points. So let me check the point. Let's check 5, comma 2, comma -11. Keep in mind that's my x, that's my y, that's my z. And so if I check with this one, if I look at my equation, I get 1 minus 5 instead of 1 minus x over 2, which equals just 2, which equals -11 plus 3 over 4. And again, substituting my x in, my y in, and my z in. So much highlighting. In this case, you'll see this equation is not correct. I get -2, but then I get +2, and then I get another -2, which means this equation is not correct, which means this point is not on that line. Well, what if I just change up these points and instead look at 5, comma -2, comma -11? Virtually the same thing. Only difference is that middle term. And if we do that, you can quickly see it will work. I get 1 minus 5 over 2, which we've already done, -2, -11 plus 3 over 2, which we've already done. In this case, we get -2 equals -2, which equals -2. Since all equations work out, yep, that point is on the line. All right, so lastly, I have a Cartesian form of a three-dimensional line. So 2x minus 1 equals 4 minus y equals 3z plus 1. Let's write it as a vector equation. And so keep in mind, each of these equals the same thing, and each of these equal lambda. So let me start by writing that. Lambda equals 2x minus 1, lambda equals 4 minus y, and lambda equals 3z plus 1. And so just to reverse what we did before, now for each of these, let me solve for the variable x, y, or z. So if I look at the first one, if I solve for x, I get x equals lambda plus 1 over 2. Over here, I get y equals 4 minus lambda. And over here, I get z equals lambda minus 1 over 3. Now, how do I put this into my vector form? Well, let me go back and look at how I got these equations. For example, if you look at these equations here, I always have a constant, or in this case a 0, and then something times the lambda. The constants came from the position vector. And so if I look back here, I want to find the constant in each, which means I just need to rewrite a few of these. For example, instead of x equals lambda plus 1 over 2, I can rewrite this as x equals lambda over 2 plus 1/2. Now I have a constant in there. I don't need to change this one at all, but I'll just rewrite it. And then over here for z, let me write this as lambda over 3 minus 1/3. And so now I can see the position vector is related to the 1/2, the 4, and the -1/3. Those are the values that were constants in here. And the dividing by 2 or multiplying by 1/2, the multiplying by -1, the dividing by 3 or multiplying by a third, that relates to the direction vector. So now I can see, okay, vector r must have had a position vector, or one possibility is 1/2 for the x, 4 for the y, and -1/3 for the z. Plus lambda times the coefficients of all these lambdas. So 1/2, -1, and 1/3. And again, if I just look at this in reverse, we'll see it works. For example, for x, I get 1/2 plus lambda times 1/2, which is what we see right there. All right, so lastly, let's determine 2 points on this line. Okay, well, one of which I can see there's a point. All right, that's my position vector. That relates to a point. So that's half my work done. So 1 point is x at 1/2, y at 4, z at -1/3. All right, that was nice. How can I find another point? Well, if I look at my equation here, I have this constant lambda that can be whatever real number I want, and that will then tell me how to find another point. So let me just let lambda be any number I want, and why not make lambda equal 1? And so then I get another point. If lambda equals 1, then really all I have is this plus one of these. And so if lambda equals 1, another point I see I have is, I'll rewrite this, 1/2 for -1/3. There's my position vector, plus 1 times 1/2, -1, +1/3. So if I add this up, I get 1/2 plus 1/2, which is 1. 4 minus 1 is 3. -1/3 plus 1/3 is 0. That said, that describes a position vector of another point. Let me now make that more formal and say 1 point is that. The other point, I should write it as the coordinates, so 1, 3, 0. There's my 2 points. And clearly, I could pick any number I want for lambda and find an infinite number of other points, and hence this equation works.